Hey, geometry, here we are in chapter 2. We're looking at conditional statements and we're going to work on some vocabulary here. Our vocabulary has some really meaty things, so I do want you to pay attention. Don't just rush past this section. Basically, when we talk about a conditional statement, right, what we're talking about is any statement that we can write in an if-then way. If you think about a conditional statement, you're thinking about the idea of pretty much everything your parents say. If you want to get this, you have to do that, right? Or if you cleaned up your room, then this would happen. So a conditional statement is any statement that can be written in an if-then form. So that brings us to the logical question of what is an if-then statement? Well, an if-then statement, well, let's just give you one, right? Here's an if-then statement. If I cut my hair would be healthy. If I cut my hair, then my hair would be healthy. I had to stick the then in there. Okay, so if I cut my hair, then my hair would be healthy. So this is an if-then statement. Literally, an if-then statement is a statement with the words if and then, and it is a conditional statement. If-then statements are actually made up of two very important parts. Those two important parts are the next two vocabulary words that we have. They are called the hypothesis and the conclusion. So the hypothesis, let me highlight that in a broad orange highlighter. And the hypothesis is the first part. It's the part that comes after the if. If I cut my hair. All right. So that's the first part. The conclusion, I'll do in blue or purple. Looks like it's purple. If I cut my hair, then my hair would be healthy. So my hypothesis is going to be the first phrase after the word if, and then the information that follows then is the conclusion. I'm going to further, looks like complicate, but I'm going to further simplify this by telling you that we're going to use P to refer to our hypothesis, and we will use Q to refer to our conclusion. And that's going to help me out in the next set of definitions. So we've got something called related conditionals, and related conditionals are going to basically refer to these things here. So here's a conditional statement that we've written. If I cut my hair, then my hair would be healthy. So the related conditional could be the converse of that particular statement, the inverse of that statement, or the contrapositive. And I'm going to let you know what they are in just a second. So my original statement can be basically broken down or represented as P implies Q. So I cut my hair implies that my hair would be healthy. And so I can look at that conditional statement and say P implies Q. But the converse would be the total flip of that. So a converse statement would be Q, right, implies P. All right. And so that's the converse. So the converse is literally a flip-flop. So the converse statement would read, if my hair would be healthy, then I cut my hair, right? If my hair is healthy, I can change the context a little bit. But if my hair is healthy, then I cut my hair. Okay? That would be the converse statement. The inverse statement keeps the PQ order, but it takes the negation of P to imply the negation of Q. So the opposite of P implies the opposite of Q. If I don't cut my hair, then my hair won't be healthy. The opposite of P and the opposite of Q are implying each other. And now the contrapositive is the inverse of the converse. All right, so remember the converse is this, and remember how we get the inverse by negating the original statement. We're going to negate the converse, right? We're going to negate both parts of the converse and say that the contrapositive would be the negation of Q, right, implying the negation of P. So let's see what that looks like. So the opposite of the conclusion, right? I know this is a little tricky, is going to imply the opposite of the hypothesis. Let's go. So my hair is not healthy. If my hair is not healthy, then I did not cut my hair. Do you see that? And so logically equivalent refers to statements with the same truth value. And I'm going to take you over to the textbook really quickly and see if we can get a little bit better insight into this. So here, okay, here we have a little bit of a nice chart, and it's on page 109 of your text. And you can see basically the symbolism that I wrote down and some examples, and the same thing with converse, inverse, and contrapositive, all right? And then a really important little blip down here, a key concept is that logic is about logically equivalent statements. A conditional and its contrapositive are logically equivalent, meaning they basically say the same thing. They're going to have the same truth value. If one is true, the other one's going to be true. If one is false, the other is false. And also, the converse and inverse of a conditional are logically equivalent. Again, the converse and the inverse are going to have the same truth value. If one is true, the other is true. If one is false, the other is false. All right, let's get back to our lesson and let's take a look at some examples. So here we are in example 1. We're going to identify the hypothesis and the conclusion. And so identifying that in these conditional statements. So let's take a look. If the forecast is rain, then I will take an umbrella. We talked about this earlier. We know that the hypothesis usually comes right after the word if, and then the conclusion is going to be followed after the word then. I will take an umbrella, and then you would just write that beside each. So the hypothesis is the forecast is rain, and the conclusion is I will take an umbrella. Not too bad. Let's take a look at this one. This one doesn't seem to have a clear if-then vibe to it, but let's see if we can make out what's going on. So it says a number is divisible by 10 if its last digit is a 0. I actually think the word if is tipping our hat and letting us know that this part, if, so we got some number whose digit is, whose last digit is 0, then we can say that that number is divisible by 10. And so I'm going to write it just like that. So my hypothesis is a number has a last digit of 0, and my conclusion is that the number is divisible by 10. So over here we're going to write a conditional in the if-then form. So we need to kind of be a little bit more attentive to what's going on. We have a conditional statement. A mammal is a warm-blooded animal. So I could see rewriting this as if a mammal is a warm-blooded, if an animal is a mammal, then it is warm-blooded. So our hypothesis is that we have an animal that is a mammal. So identifying the hypothesis and the conclusion, I then can simply write this as an if-then statement. And so I'd write if an animal is a mammal, right, then it is warm-blooded. Does that make sense? I hope it does. Sometimes I get a little confused, honestly, figuring out which one is the hypothesis and the conclusion. Just do your best. It's all good. You know, we'll make it make sense. Let's take a look at this one. A prism with bases that are regular polygons is a regular prism. A prism with bases that are regular polygons is a regular prism. So to me, it looks like we've got like a situation where we're saying that if we have this situation, prisms with regular bases, then we can tell that those polygons are regular prisms. So I'm going to write it just like that. So I've changed it a little bit, but basically prisms with bases that are regular polygons, those polygons are regular prisms. I know that seems like a mouthful, but I would write it if prisms with bases, if you have prisms that are bases, golly, this is a tongue twister. If you have prisms with bases that are regular polygons, then those prisms are regular prisms. Blah, I said it. Let me write it. Boom. All right, my friends, it is written. All right. If you have prisms with bases that are regular polygons, then those polygons are regular prisms. All right. Let's get back to where we were. All right. Nope, let's not do that. I'm not having a good success with this thing. So we're going to look a little bit at a truth table, right? We talked about truth tables and conditional statements. And so here's what we can know. If you P and Q, so we're thinking about a conditional statement, P implies Q. If P and Q are true, then that statement's true, which makes sense. If both of those things are true, if your hypothesis and your conclusion are true, then that statement is true. If your hypothesis is true, but your conclusion is false, then that statement overall is false. Notice that this is the only way to get a false statement is if the hypothesis is true and then the conclusion is false. All right. Now here, check this out. The hypothesis can be false and the conclusion true, and still your overall statement is true. And here also, now this one's probably even more tricky. Your hypothesis can be false, and then your conclusion can be false, and your statement can therefore be true. Let's see if we can see some examples that'll help us feel more confident about this. So let's look at example 3. We're going to talk about the truth of conditionals. Determine if the truth value of each conditional is true. Explain your reasoning. If false, give a counterexample. So I'm going to kind of put it in this PQ form, right? So we know we've got P, we've got Q, and then we want to see if, not G, nothing about G, my friends. We want to see if P implies Q is true. So let's go. If you divide an integer by another integer, is that a thing you can do? Yeah, so that's a true statement. The result is also an integer. That's actually false. That's actually false. And we can go back to our chart and see our chart says if you've got a true hypothesis and then a false conclusion, then your statement is going to be false. And so our statement is false, just given that thought process. But let's think about it, because we need to actually come up with a counterexample. The counterexample is pretty simple. If you divide two integers together, so if I divide 5 by, let's say, 2, the result is also an integer. Remember, integers are negative and positive whole numbers. So 5 and 2 are considered an integer. When I divide 5 by 2, I get 2.5, which is not an integer. So this is my counterexample for this situation, all right? This is the example that proved this statement false. And so there we go. All right, so hopefully that makes sense. Let's look at this one. If next month is August, then this month is July. So for the sake of what we're going to talk about, I can say that let's pretend it's August, right? So this is P, this is Q, and we want to know if P implies Q is true. Well, if this month is August, let's say that is true. Then, I'm sorry, if next month is August, let's say that is true. I know it's not right now. Then this month has to be July. That would indeed be true if next month were August. This month would be, and therefore it's true. Let's try it again. If next month is August, well, that's false because it's not. Then this month is July. That's also false because this month is October, right? But that also means that this is true. And we can think about that in terms of this right here. When our hypothesis is false, our statement's always going to be true. Our statement's always going to end up being true because our hypothesis is false. I know that feels uncomfortable, but I guess if you start off with, if you think about it, if you start off with an erroneous or made up premise or a premise that's not true, then it doesn't matter. Then the conclusion doesn't matter, and then you can say that the whole thing is it's a true statement because it doesn't apply. I don't know. I feel like I understand it, but I feel like I'm not explaining it well. That's okay. We're going to get to the bottom of this. Let's look at this next example. If a triangle has 4 sides, then it is concave. Well, this P is clearly false. It is, and since it's false, then we know that this statement is now true. So because this guy is false, Q doesn't matter at all, and I can say overall that this statement has a positive, a truth value of true. I'm going to get into the last example in the next video. I'll see you soon.